In this video, we're going to be looking at the final type of deviation from the octet rule that we can see with covalent Lewis structures, the first example of which is nitrogen dioxide here. If we start by our normal procedure of counting valence electrons, we know that nitrogen has 5 and oxygen has 6. If we count the total number of valence electrons that this compound has, we would get 5 from nitrogen and 12 from the 2 oxygens, which gives us a total of 17 valence electrons. This is rather strange because it's an odd number, and if the only way that we can add electrons to a structure is by adding bonds or lone pairs, this number should be even. So how exactly do we deal with this? Well, nevertheless, let's try drawing this following the standard rules. So again, we find our central atom, which is nitrogen, because nitrogen starts with 3 unpaired electrons, whereas oxygen only has 2. Next, let's connect the oxygens to the nitrogen with single bonds, which means that I just added 4 electrons to our structure, meaning that we have 13 left. Secondly, let's put oxygen's lone pairs back on, meaning that we add 2 lone pairs to each oxygen for a total of 8 valence electrons, and that means that we have 5 remaining. I haven't put nitrogen's lone pair back for reasons that we'll see later on. Now, normally at this point, we would add in our double bonds, but if we do this, we see a problem. Adding 2 double bonds means that I just used 4 valence electrons, which means that there is 1 electron left and nowhere to put it because all of these elements in the structure now have 8 valence electrons, and since none of them are big enough to have an expanded valence shell, we cannot put this electron anywhere. So let's turn back and rethink our approach about adding in electrons. Now, if we can't add in 2 double bonds, well, maybe we can put one of the double bonds back in, and instead of adding a second double bond here, we can put these electrons on the oxygen and act as a lone pair. That way, both of the oxygens have a full valence shell. Each of them have 8 valence electrons now, but nitrogen, it only has 6, which means we can take this extra electron and add it to nitrogen as an unpaired electron like this. Whenever we encounter a compound that has an unpaired valence electron, as on the nitrogen we see here, this structure is what we call a radical. And there are a few reasons why radicals can exist. Number one, if we look at formal charge, we see that the formal charge of this compound actually balances out rather easily. We know that oxygen starts with 6 valence electrons, from which we subtract 4 for the lone pair electrons, and 1 electron per bond, which is 2, so this oxygen has a stable formal charge of 0. This oxygen here, again, starts with 6, from which we subtract 6 because of the 3 lone pairs, and 1 for the bond, meaning that this oxygen has a -1 formal charge, which we can indicate with a negative charge here. If we calculate the formal charge of this nitrogen starts with 5 valence electrons, from which we subtract 1 from this radical here, and 1 for each bond, which is 3, giving nitrogen a +1 formal charge, which we can represent with a positive charge here. And if we add the formal charges together, -1 + 1 + 0, the formal charge ends up being 0, which matches the charge of the molecule. So from formal charge perspectives, we're good because the charges equal the total charge of the molecule, and the negative formal charge falls on oxygen, which is the element with the highest electronegativity. In fact, this is one of the reasons that allows radical structures to exist. Pretty much every stable structure that contains a radicals is going to have at least one element, if not all of the elements, with a high electronegativity, because the higher electronegativity is, the more attractive to electrons they are, and the more that those elements can help stabilize the extra negative charge that comes from having an unpaired electron like this. The second reason why structures with resonance or with radicals can exist, Freudian slip there, is because we see that resonance is also present. If we take one of these lone pairs, we can move it down and convert it to a double bond here. And again, normally this would mean that nitrogen would have too many valence electrons because nitrogen can't have more than 8 valence electrons. But if we take the electrons from this double bond, break it, and move them to this oxygen here, now we could have them as a lone pair. And if we redraw the structure after this electron movement has taken place, now we see that the negative charge, or the negative formal charge rather, is located on this oxygen here. So the idea being that resonance can also help to stabilize the extra negative charge that occurs whenever we have a radical, because the negative charge that comes from the extra electrons is not only on the oxygen on the right, nor is it only on the oxygen on the left. It is distributed between the two oxygens. So if we draw the hybrid structure, remember that only bonds that appear in both structures can be drawn as full bonds, whereas bonds that are moving between the two structures we represent with a dotted line to indicate that they are sometimes there and sometimes they aren't. And again, only the electrons that are present in both structures are shown, which means that we can only add 2 lone pairs to each oxygen like this. But again, rather unusually, the radical electron, the unpaired electron on nitrogen, does appear in both structures, giving us this rather unusual looking hybrid structure here. So, in conclusion, a radical is what we used to describe any Lewis structure that has an unpaired electron in its final structure due to an odd number of valence electrons. Radicals are possible because the formal charge of each of the atoms balances out, because the elements within the structure usually have very high electronegativities that allow them to hold that unpaired electron, and because we can take the charge and distribute it over multiple atoms like this using resonance in order to stabilize the structure. In the next series of videos, we're going to look at the quantum mechanics reason using electron configurations to explain how bonding works, which will also help us explain phenomenons like resonance, as well as expanded valence shells and radicals.